to answer some of these questions. So new unit, unit number 6, sampling distributions of proportions. So we're now kind of shifting gears away from just finding data and now using that information to make guesses or inference back to a population. So we're actually doing the stuff that makes people money, making predictions based on smaller samples. Okay, so there's not really anything outside of these new rules really to teach you about how to find probabilities or how to find percentages. It's now just applying it and using that information to make a guess back to the population from whence it came, if you want to be fancy with your English term. So we're not going to do this activity because normally we would do this in person and we got time, we can play with the pennies. So we're just going to hypothetical discuss this. If I gave everybody a penny and asked them to toss it 20 times and the number of heads that they got, what they would do then is go on the board, mark on a number line, you know, I got 9, I got 7, I got whatever. If I got everybody in class to do that, just guessing out loud with very limited to no experience on this, what kind of shape do you guys think I would get from the graph if we did that? Okay, we got a guess for a rectangle. What else? Any other guesses? Where's my chat here? There it is. No, we all agree with Matthew. It's a rectangle. It's close to a rectangle. It's not a bad guess. It's actually going to be more normal, and here's why. So let's say hypothetically we've got this, you know, situation that we're going to do. If I ask, you know, Kate and everybody else in here to flip the coin 20 times, she could get anywhere from no heads all the way to all 20 of them, right? That's her only possibilities. Obviously, it's discrete because it'll land on a particular number. That's not important right now. But most people are going to be pretty close to where? Around 10. Because we expect the probability of the coin to be close to 50-50. All right, so we're going to have a lot of people in this range between, like, say, 8 and 12. That's where a majority of my people are going to be at. We'll have a few over here, and we'll have a few, like Jackson will be the one kid that gets like 18 because he's that guy. All right, but we'll have, you know, over time, as we start to do all this, the graph's going to start to do that. So that's kind of the whole objective of this unit, is to take a population that we don't really know the shape of it, all right, and then bring it into a sample by taking multiple samples and getting a new distribution. So his guess was actually a fairly good guess because he was thinking about what the population is going to be. So over time, you're going to have two answers. You're going to have this would be the group of heads and this be the group of tails, and they should be fairly accurate because we're flipping it. So that's not a bad guess. This is what the population looks like. But the samples, each of those samples of 20 are going to create a different graph, which is going to be normally distributed. So today our goal is going to be to take samples in such a way that we get this graph so that we can start doing our probabilities that we learned in Unit 5 on it and make conclusions and predictions. All right, so I'll show you another picture of that a little bit later, but just kind of keep that in the back of your mind. As we're doing this section of notes, we're trying to work our way into that direction. All right, so it should be approximately normal, blah, 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 same thing I just said, because all of the possible combinations of 20 are going to create that normal graph. All right, so sampling distribution. This word is phrase we're going to use a lot. So this is the shape of all of the samples that are possible from the population. All right, so again, it's the shape of all the possible values from a sample that has the same size from the same population. Okay, so this definition is at the very top of your notes. So sampling distribution, again, is just that shape of the graph I'm going to get from all the samples put together. So in this case, we were taking samples of 20 coin flips from basically an infinite population, and we were creating a new graph that was approximately normal because most people are going to be toward the middle and less people are going to be away from that number 10 because we know that it's 50-50 either way. All right, so in the case of the pennies, it would be the distribution for all of the different sample possibilities for the size of 20 for that particular population. So you're going to see two symbols here on this first part of the notes. You're going to see the letter P, which represents the percentage or proportion from a population. And you're going to see the P hat symbol, which means from the sample proportion. So we're going to use both interchangeably. They're right there on your notes. You don't have to write anything down if you printed these off or you're looking at your deal there. So just pay attention what the characteristic is. It'll tell you which one it's talking about. So here's that picture again. It's kind of fuzzy, but basically it's saying you have this population up here. It has a percentage. So the coins had a percentage of 50% heads or tails. Like we know that's true. We've done experiments with that. Everybody in the world kind of agrees it's a 50-50 shot, everything else being equal. If I start to take samples of 20 from that population, each one of those samples of 20 are going to have their percentage. So the first one might come out with 8. The next one might come out with 12. The next one might come out with 11. Each sample is going to have a different result. It won't always be 50-50. But as we start to stack up all of the different possible samples, most of them are going to center around our 10. Because 10 is what we'd expect to get out of 20, 50-50. We'll have some samples that'll be lower than that, 2, 3, 4 heads only, and some that'll be really, really lucky, I guess, and have more heads, be like 13, 14, 15. But overall, the more of these samples we take, the more our graph is going to become normal. Once we figure this part out here, once we get our graph normalized, so to speak, we can start using all the probabilities we learned last unit and making predictions and that kind of stuff. So that's what we're kind of working towards. That's where we're going to be. So this picture is going to stay on the slides if you want to go back and look at it later. I'm not going to make you draw this all the time. I don't even care if you really got much from it. It's more of just for those that like to see visually what's kind of going on behind the scenes as we're doing this stuff. All right, so let's practice with an example here to kind of see how this works. So we have this population of 6 people. We got Alice, Ben, Charles, Denise, Edward, and Frank. So what is the proportion of females, or what is the percentage of females in that population of 6? 2 out of 6, very good. All right, so it's written on here as 1/3, but same thing. Yay, there's everybody. All right, so we're going to assume that Alice and Denise are the girls, everybody else is the guys, so we got a 1/3 or 2 out of 6 proportion. So this is my population percentage. So what is the parameter of interest in this population? The proportion of females. That's what I'm interested in. I want to take samples in a little bit from this population, figure out my numbers from my sample and say, this must be true for all 6. That's kind of what this unit's about. So we're going to draw sample sizes of 2. Obviously, this is an extreme scenario where I could just do all 6. It'd be easier. But in real life, your population is huge. So this is why we're kind of talking about this. So we're going to pretend like we don't want to do a census on all 6. We're just going to grab 2 people at random. And based on what we get over and over again, that's going to tell us everything we need to know about all 6 of them without actually talking to all 6 of them. So how many different samples are possible of 2 out of this group of 6? So you have to remember back to our combinations. The beginning of December. You don't have to do this very often, if at all, on any of these problems. I'm just letting you guys know where we're getting these numbers from. So there's 6 people. I want groups of 2. How many different ways can I do that where order does not matter? 15. I can now find all of the different proportions or percentages for each sample. Okay, so the first sample, Alice and Ben, the ratio is 0.5 because there's 1 girl, 1 guy. All right, Alice could also be with Charles, 0.5. She could be with Denise. There's a 1 because they're both female. She could be with Edward, 0.5. She could be with Frank, 0.5. So these are just the ones with Alice in it. Then we've got Ben with Charles. All right, so it's 0 because there's no girls. Ben and Denise, Ben and Edward, Ben and Frank, Charles and Denise. All right, we got them all on here, all 50. So these are all the percentages of male to females basically in these groups. If I added all of these up and I took the average, I'm going to get 1/3. So there's a neat little trick that just happened here. Whatever my population's average is, it matches my sample's distribution because I'm pulling all of the different little populations from the same group. So overall, if I add them all up, we're going to get back to our original average. So that's going to be a neat little trick here in a minute when we're doing these things. No matter what samples you're getting, the average that you're supposed to get of all of the samples put together should be the same. All right, and that's on your formulas. If you guys look at your formula charts, it says the little u with the p hat equals p. It's a little fuzzy, but that's what it's saying. Now, what does change, though, is the standard deviation. So the standard deviation of the original population will be different from the standard deviation of your samples because of how many people are in your group. So that's going to affect the spread of the data, but these 2 things are always equal. So whenever we're doing these problems, if I just come out and tell you, hey, the population has a percentage of whatever, then you know that all of your samples that you take are going to have the same average. All right, now you might get a sample that doesn't meet the average, but altogether their distribution, the shape of all of them put together, we'll be back to that. So all of those 20 flips on the pennies, not everybody's going to get 10, which is the average. But if I took them all together, we'd come back to 10. All right, so there's your formulas. If you can't see them, you can write them in darker on your notes. So average equals the percentage equals the population's percentage. And the standard deviation of the sample is now this. So you have to convert it to match your new sample size. All right, so they're on your formula chart. The one on the far right is if you don't have the population to deal with, and you can use it for the sample. It's the same formula. All right, so the standard deviation of the sampling distribution equal the equation. In this case, it doesn't, because we don't have the right size sample from the population. So what we're going to start talking about next is the assumptions. So before Matthew can get all excited, dive in and start figuring out I know he's super excited. Before he can start figuring out all the samples information, he has to check 3 things are true. All right, so we're going to look at this here in just a second, but you do not want to sample more than 10% of your population at a time. It's a statistical rule that prevents you from having too much in your sample and you lose your independence. And we don't want to lose independence, because then our probabilities start changing and everything starts getting weird. So in this case, our actual standard deviation didn't match. So we have this little normalizing formula. It is not on your notes. You don't have to panic with it right now. You don't need it for today. When we do need it, I'll go back to it and remind you guys. But basically, if you have more than 10% of your population in your sample, then you can use this normalizing or correction factor and fix it. Don't worry about it today. You can write it down if you want to, but we're not going to use it today at all on the notes, and we're not going to use it today at all on the homework that I can see. But it's there. We'll talk about it later when it comes up. Like sometimes the notes just throw stuff at you don't need just yet. Right? And we had to do this here because we used more than 10% of our population. And if you're completely 100% confused, you're okay. Don't worry about it. I'm going to go through some examples with you. It'll make life a little bit easier. It's okay to be confused right now. I'm just throwing a bunch of weird stuff at you. All right, so in order to calculate the standard deviation of the sample there, we need to make sure that we do not sample more than our 10% of our population. So there's a way to check for this that we're going to go through with the assumptions. So let's look at the assumptions so that we can actually start doing these problems. All right, so assumption number 1, your sample size has to be less than 10% of your population. This is to secure the fact that your samples are independent of each other. So you may or may not remember way back, I kind of casually said something about this when we talked about the light bulbs on our special probabilities. And I said, if you pull 2 light bulbs off the shelf, you're not going to change the chance that the next ones have the 5% being broke. And Matthew was like, well, how do we know that? I think it was Matthew that I said, how do we know that the percentage doesn't change, right? That's because the 2 light bulbs were less than 10% of the population. So it was okay to assume that the overall proportion was not going to change on that. So we're going to double check those today. I know what I kind of briefly mentioned it back then. Today we're going to check it. The other 2 things we have to check guarantee that we have a normal distribution. So all of our little samples, if you go back to that picture, need to make a normal graph. If they don't, everything we're about to do is worthless and a waste of time. So in order to check that our data is actually normal, all of our little samples put together, these 2 things will have to be met. The fact that our sample size and our percentage is greater than or equal to 10, and that our sample size and the complement of our percentage, 1 minus p, is greater than or equal to 10. If you check all 3 of these things and you're good, then you can work the problem. If you don't want to do the problem and you're hoping that Mr. G snuck in a trick one, then you want one of these to fail. Then you can't do anything else. So what we're about to do will not work if all 3 of these are not true. So part of your requirement this unit, like I said, this is going to be a little tedious, is double checking these things before you start. All right, so let's do an example together so you guys can actually see what the heck I'm talking about. And then we'll stop and see if you guys got any questions so far. Because right now, I'm sure for most of us, this is all just a foreign language. I'm like, blah, 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 blah. So let's look at an example. All right, so yeah, real quick, sorry. The reason why we want to check for those last 2, if you're curious, some of you guys want to know. I can't assume that my distribution is normal if my sample size is too small. So if I only had a sample size of 10 at a percentage of 10%, then my graph's going to look like this. You can graph it in your calculator later if you're really curious. This doesn't help me. I can't do anything with this graph other than to say, oops, it's skewed. That's nice. It tells me nothing. What I want instead is a sample big enough that I can make this distribution with the same percentage. So in the case of us having 10%, we would need about 100 to make sure that it works. All right, so there's a fine balance between too big, which makes things not work, and too small, which makes things not work. And luckily, most of the problems we are going to work with have all that covered for us. We just have to check it off the list so we look like we're good statisticians. So it's not like Kate has to create a bunch of stuff from scratch. It's all going to be in there. We just have to kind of go through the process of saying, hey, we know that this is supposed to be true. All right, so don't panic. You're not going to be creating things from nothing. All right, let's look at an example. Enough of Mr. G talk. Past experience, a bank believes that 7% of people who receive loans will not make payments on time. The bank recently approved 200 loans. Are all of our assumptions met? So that's the first question we got to ask. That's part A on your notes. Part B says, what are the mean and standard deviations of the proportion of clients in this group who may or may not make payments on time? And finally, letter C, can we actually make a prediction of the amount of people that, or the chance that people over 10% are not going to pay their loans? So let me write down two things that are important, then we'll get started here. So our percentage for the population is 7%. Our sample size from this particular problem is going to be 200, because I'm going to use the 200 people that the bank recently gave a loan to as my sample size. All right, so we're going to answer these questions in your notes, A, B, and C. If you got them in front of you, you guys can follow along. So this is all we know for sure that it's true. What we want to ultimately find out is the probability. I'm going to put this over here so you don't forget that our X value, all right, or not our X value, I'm sorry, the probability that our sample proportion, I got to get used to the new notation, is going to be greater than 10%. So basically, I'm a bank manager. We've just released 200 loans to people. What's the chance that over 10% of them default on it? If that happens, I make no money. As the bank, I lose money. We make money when I loan Matthew $100 and he has to pay me interest. That's how the banks get rich. So if Matthew spends $100 and then defaults and has to go to jail or whatever, then I don't make anything, right? Matthew still got what he wanted, but he's in jail and I got no money back. All right, so everybody, we don't want that scenario. That's not good for anybody. So we're going to, based on this information, figure out the likelihood that this is the case. Because maybe my manager or branch manager says, I'm okay for up to 10%, but anything past that, you're fired. Okay, so I'm stressing it. So we have this population percentage right here. So assumption number one says, is your actual population, so for our assumptions, all right, so for number one here, is my population actually larger than 10 times the sample size? So is my pop greater than 10 times 200? Now, when you do these, so that you don't stress yourself out, panic, worry, and make these problems harder than they need to be, think large on your population, like the largest scenario you can think of. Okay, so don't think of Bank of America by the Kroger at the high school that does like 2 people a day because they're slow and nobody works there. Think of like Bank of America, like worldwide, they do a lot a day. You just don't see it. So what we want to do is check that our population is greater than, in this case, 2,000. I'm going to say, yes, I bet you the old Bank of America handles more than 2,000 loans at any given time. They're a big old bank. So don't get too caught up with, well, wait a second, Mr. G, how do I know that they don't do like 1,500? Now you're making this way harder than it needs to be. 99% of the time, this is going to be true. All right, the only time it won't be true is if it's like blatantly obvious, like, wait a second, we don't have that many people that do this, or there's not that, like, you will know. Okay, so don't go hunting for it is what I'm saying. So assumption number one is met. Now we got to check, so this helps us check that this is independent. So we're good now. We need to now check that we have a normal graph to work with. So the next two assumptions have to be met. So assumption number two, so that's number one. Number two is n times p greater than or equal to 10? So my sample size is 200. My percentage rate is 0.07. All right, if I do a little bit of math in my calculator, I get 14 with that. So is 14 greater than or equal to 10? We're good there. We need to make sure our sample is big enough to allow it to be a normal graph. But it also has to be small enough that it's not too much of the population. So see, there's this fine line in between that we're bouncing on. All right, last assumption number three. Usually if this number two is true, number three is true, but we still got to check to be sure. Is n times 1 minus my percentage greater than or equal to 10? Meaning, is 200 times 0.93, right? Because it's 1 minus that, which is equal to, if I did my math correct earlier, 186. Is that greater than or equal to 10? So all of these have to be true before I can do anything. All right, all have to be true before anything else. Do not start working on the problem until you've written out and shown me that these three things are true. AP people are going to check for this. We're going to check for this. You're going to practice doing this enough, it'll become second nature. But just know that you have to show all of these assumptions. So this one shows independence. You don't have to write this step out. And these ones show that it's normal. Those two do. So now I'm working with a sample size or sample sizes, since we're doing multiple of these, that fit my independence. So I'm not affecting percentages by taking too many off the shelf. And I know I'm doing a large enough sample size that I'm able to make whatever the graph was originally with the population. All right, so if we think about it, the graph for this is probably something like, you know, hopefully it's like that, or skewed one way or another. I have to think about it a little bit more, but it's probably not normal. Okay, we wouldn't assume a normal distribution for defaulting. It'd be a small portion of people on one end of the spectrum. I can't think right now if it doesn't really matter if it's going to be skewed left or skewed right, but it's probably skewed. So now we're making it normal by taking these samples in such a way, like we did earlier with the graph. So now, what was the question that we wanted to do? Now that we've done A, we need to figure out B. Matthias, did you have a question, or are you just popping on the tail?
Oh, yeah, I was just wondering why we had to multiply the sample size by 10. I still don't get that part.
That guarantees, so 10 just means if I multiply this by 10, that it's smaller than, that it's only 10% of my population. It's just working it from the other end of the deal.
Okay.
So since I don't know what my population is, I just multiply
Right.
my sample size by 10 and go, is my population at least this big?
Yeah, okay.
Does that make sense?
Mhm.
Yeah,
Yeah,
good
thanks.
question. Yeah, because there's a lot of things we won't know about our population, right? Because we're not going to go do a census. So we've got to kind of play with this from the other side of it. All right, so part B, what are the mean and standard deviations of my new sample distribution? All right, so we're done with the population. We got what we need from it. Now we're going to start looking at the sample. So remember what I told you guys in the notes. All right, it's normal now. We've proven that. So we know what kind of distribution it is. What's the average going to be if you use your formula? It's got to be the same thing. Because if you're pulling all of these samples from a population, they're all going to average back to what they have. Okay, so the average for this is 0.07. Now, the standard deviation is different. So you got to use your formula over there. The standard deviation of your p hat now is going to be equal to the square root of p times 1 minus p over n. So what is p? 0.07. What's 1 minus p? 0.93 divided by, what is our sample size this time? It's 200, right? Yeah. All right, so we okay with where I got my numbers there? Okay, so you can use this in the calculator. If you guys want to see the way I do it, I make this fraction in the calculator. So I hit the second x squared button, it brings up my square root. And then I hit the little green alpha button and the y equals and press enter and makes a fraction. That's what I do. You don't have to do it like that, but it just makes it easier for me to type things in and organize it. So now I can do 0.07 times 0.93. Like now the calculator knows those two go on top, just like I have it right here. You don't have to do parentheses. You can do the time symbol, whatever you want. It just makes it organized. And then at the bottom, put your sample size, and that's your new standard deviation right there. So the old one was something else. We don't care. The new one is this one. So I'm going to write over here that we have 0.01804. So I've got a standard deviation and an average for a normal graph. So that's part B. Part C says, what is the probability that your p hat, your sample size, is going to be greater than 1%? So do we use number 2 or number 3 when we do second bars now? Let's see who paid attention from Unit 5's test. Don't look at me like that, kid. I'm asking the question. She's over here like, I don't know, Mr. G. So do you use normal CDF or do you use inverse norm? Normal CDF, right? Because we want the percentage. So number 2, Derek's over there going, come on, Mr. G, it's number 2. He's correct. So what's my lower limit? 0.1, because I want 10% or more. So what's my upper limit? Infinity. What's my average? So this stuff should be familiar from what we did on the last test. You just have to get here. Now that's the new trick. 0.01804. Are we okay? So if you press enter, it's going to give you the likelihood that your sample of 200 people are greater than 10%. So that means I'm looking at 0.0482. So if I'm the bank manager and I just issued 200 loans and my boss comes by and says, hey, if more than 10% of those people fail, you're fired. I'm like, ooh, yes. So I go back and I look, and so what's the chance that more than 10% of those people default on their loan? Here's my percent. Okay, can I live with a 5%-ish risk of that happening? Maybe, maybe not. You're the bank manager, you decide. But now we're getting into that part of statistics now. We're no longer just looking for the answer. We're going to start interpreting, does this make sense? Are we okay with this? Do we fire somebody? Do Do we close the company down? Do people get new jobs? Do we raise minimum wage? Do we add more vaccines? Like all that stuff now we can start answering because we're going to be looking at stuff like this. So it's going to get a little heavy on some things because we've got all these little steps. We've got to start putting pieces together, and now we're starting to see the whole puzzle come together. And we did a little bit of graph analysis. We did a little bit of probability, a little bit of sampling design. We're kind of putting all the pieces in. Okay, so if it goes too fast for you or it's a lot, then hit the brakes with me and say, Mr. G, explain that again. And I'm happy to like bring it back in from where we got it before. All right, questions? What's going to get some of you guys at the beginning is these steps. You can't forget to do these. You got to verify your assumptions. And they're always, well, I shouldn't say always, they're mostly going to be true. There's very rare times that they're not going to be. Yes, ma'am. Yeah, so I did second vars number 2. And then 0.1 is my lowest limit because I'm going to the right. So I want this or bigger. What'd you get? And everything here is exactly the same? Interesting. The only thing I can suggest to you is hitting the second mem 712 and just giving it a good clean reset in case somebody did something squirrely in it early. Okay. With those on-level students using it, I mean, who knows me? To try to figure it out would probably confuse you more. Okay, so let me go back to the notes real quick so you guys can see. There's your assumptions met. There's your answer. There's your new standard deviation. Check, check. Okay, so Mr. G showed you how to do that on paper. So if you're looking at the slides later, there's my new normal distribution. She left it in the square root form. I converted it to the decimal of 0.01804. And then there's our probability statement. Notice it's got a little p hat symbol now, not x, because we're looking at proportion samples. And then there's the chance that it's going to be over 10%. All right, let's try another one. We'll do another one together, and I'll let you guys try numbers 3 and 4. So number 2, suppose one student tossed a coin 200 times. So Kate comes to me and goes, Mr. G, I just tossed this coin 200 times. I only got 42% of them to be heads. Do I believe Kate? That's the question. Kate's like, you better believe. She's sitting right here, so we're going to find out. So there is our assumption. So let's write these down on a piece of paper and then check them and make sure we understand where they got for. So you start off with your assumptions because before you start working with anything, you need to make sure that everything about your distribution is true. So number 1, we need to check that the population is greater than 10 times n. So population greater than 10 times n. So what is the n on this one? 200, very good. So Kate just said her sample, she flipped the coin 200 times. I'm just using Kate's name, so it's not just a student. So 10 times 200 is going to give me what? 2,000, very good. So since the population of coin flipping is technically infinite, we're good there. So see, think big, okay? If I had each of you guys go home and flip the coin 100 times, we'd surpass the population needs. It'd be easy. So it's not that difficult. So assumption number 1 is met. Assumption number 2 and 3 is the samples from a normal distribution. So you start with n times p. So n times p has to be greater than or equal to 10. All right, well, our n is 200, and our p in this particular situation is what? Using the population on this one. So what's the percentage here? 42, very good. Actually, no, I'm sorry. That's the one we're going to be testing. I 100% lied to you. It is 50, because what is the population of flipping the coins anytime? 50-50, right? So that's the one we want to use, 0.5. I apologize 100%. I just confused the heck out of you. All right, so 200 times 0.5, is that bigger than 10? Oh, we got yes. Okay. All right, and then do it again. All right. Sorry, yeah, and do a 0.5 for the other one. Well, Mr. G, it's 1 minus p. Well, 1 minus 0.5 is still 0.5. So n times 1 minus p is greater than or equal to 10. So it's 200, again, greater than 0.5. The answer to that is yes. All right, so I didn't mean to confuse you guys. I apologize. I got ahead of myself. All right, so here's my paper version if you want to look at it. Assumptions. Check your population, check your normal stuff. Questions on that? All right, so once you know these are all good, all right, again, all have to be true. If it's not the case, don't move on. Then you go to the next step. What is your sample distribution? Okay, we can use this from the population for our average. They never change. Dang it, I'm sorry. G's having a bad That's a bunch. We can use our population's percentage, because what is our population percentage? 50%. And what is our new standard deviation going to be? How do we figure that one out? You got to do the little formula over here. So it says P times 1 minus P and the square root here. So that's 0.5 and 0.5. All right, so that's P, that's 1 minus P. Over, what's Kate's sample size? 200. And I do apologize. 0.5 is our population percentage. 0.42 is what we're testing. I've been doing this already 5 times a day, so my brain's hurting. All right, so you can type these in again. Second, x squared to get your square root symbol. Alpha y equals, get your fraction if you want it. It's 0.5 times 0.5 at the top here. Underneath, it's 200. Ta-da, we get our new standard deviation. So 0.0354 is what I'm around it. Probably shouldn't round it, but what are you going to do? All right, so let me stop right there since I just confused everybody by being stupid. Are you guys okay with this? I didn't mean to confuse you. So apologies all around. It should be 0.5 here because that's our population proportion. How do I know? When you flip a coin, what's the chance you get heads or tails? All right, so now that I have this, now I can finally do what I was trying to figure out earlier. What's the chance that Kate got 42% or lower, basically, is what I care about. Okay. So less than 0.42 this time, not more than. I know it's likely she got more than. I want to test what's the chance she got this or less. All right, so now I can go into the calculator. We have something to test. We go second, vars number 2. All right. This time our lower limit can be infinity. That's fine. Our upper limit this time is going to be 0.42 because that's the highest I want to calculate. What's our average for this? Should be at 50%. What's the standard deviation? 0.0354. And if you add more decimals, that's fine. All right, so what does this tell me? It's just a weird decimal, Mr. G. What does that mean? What this means is, with Kate's sample of 200, the chance that she got an average of 42% heads, or a proportion at 42%, that's the chance. All right, we calculate it into percentage terms. Do I believe Kate? No. Anything less than 5% is very, 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 very weird. Yes, sir. Please ask. I probably confused the heck out of you. I apologize. Right. That's our
probability statement says that we found less than. So the probability statement is
this part right here.
Used to write the probability of less than like 50. Now we're writing a percentage.
Yeah, we're just replacing our x value with a percentage.
So I guess what's confusing is like, does that include like if you were to get 41%?
Yes.
40%?
Yes.
So is that really what we're looking for? Only looking for?
Yes, because this is a continuous distribution that is normal in shape. And so what we're looking at is the shading under the curve still. And so right down the middle, this is what we would expect, 50%. All right, anything over here starts to get rare. Like if somebody came back and said, I got 85% of them are heads. Okay, that'd be over here on this side, kind of outlier. She was over here at 0.42. So basically we want to know what's the chance that you get anything from there or less. So we're including them all. Because remember, you can't do equals with your continuous distribution. So we would never say equals to something. So it's like a percentile, a chance to have this or less.
Wait, why can't we use normal PDF if it's asking what's the probability that she got what she got, and that's
So
0.42?
you're never going to use PDF ever in the class. So you can just ignore option number 1. Like if there was a way to delete it, I'd have you delete it because you just don't need it.
Okay.
Because we're dealing with a continuous. You guys are asking great questions, by the way. I'm not at all upset. These are great questions. I'm going to try to explain them the best I can with where we're at so far in the notes. So you still may be confused, and I apologize. So what we're looking at is basically creating a region on the graph where we start to believe things are a little weird. So what we're going to learn in the next couple of lessons is this is the area of rejection, AREA of. Typically, what we look for as far as, and this is may or may not answer your question, Matthias, so I apologize in advance. Typically, what we're limiting ourselves to when we do this is a 95% or 90% confidence interval. where we have only 5% of the area on either given side of the graph or less be something that's weird. Everything else we can chalk up to random happenstance. So if Kate's 42% happened to fall into the, hey, it just happens, it's random, then we could just say, yeah, I believe her, it happens, okay? What
So a value for that would have been like 6% perhaps?
Yeah, somewhere it'll be, we could reverse engineer it if you wanted to. It's not important now, but we could figure out what that X value is, yeah.
Okay.
But what we're saying in this particular problem, because these are great questions and we will answer these a lot more detailed as we get moving. What we're saying is her 42% is so far off what we expected. This is what we expect. Anybody that takes a sample of 200 coins should give me this answer, because that's what the population is. It should be 50-50, all right? I will allow for a random chance of 48 to 52% probably being the most likely variation. I don't know. I'm not doing the math on that now, but we could figure it out. But 42 seems a little further outside the range than I would expect. So when Kate comes back and says, well, only 42 of my coins flipped up heads, which means 42% out of 200, so that's going to be 84, if I'm doing my math right. That seems a little weird. She should be closer to 100. So what we're saying with this analysis, without going into too much detail, is she's so far away from the average that the chance of her getting that, based on this being our true population proportion, is only 1%. So what we haven't learned yet, and we'll start learning on Thursday and Monday next week, is typically our threshold is, and we'll talk about this actually at the very end of the notes today, is 5%. Anything less than that is a red flag. Something happened. Anything more than that, it's random stance. So if she'd come back in the 42%, this number came out to be like 0.067, like it was a little bit higher than 5%. I would have went, it's a little weird, but it's within my normal range of random probability. So what we're doing as statisticians, we're saying, and we'll see more of this as we go, it's likely that I get a weird sample on occasion. Like I could accidentally grab the tallest kids or the shortest kids or the smartest kids or the dumbest kids or whatever. Like it can happen. We did that with the jelly bubbers. Some of you guys had the really big jelly bubbers and some of you guys had really small ones, so your percentages were off a little bit. And we know in statistics that the randomness of that, it happens. But if it gets to be so weird, like it's so far away, then we start to go, why is that? Is the original, and this is the questions we're going to be asking here in the next couple of weeks, is the original percentage wrong, or was the sample, screwed up? Because this shouldn't happen. Okay? Kate should not come back with 42%. I think 46, 47 is probably where the threshold. That's about as low as she should go if she did everything right. So did she flip them weird? Is her coin screwed up? Or is the average not 50%? I don't know. So this tells me that there's a red flag. These are great questions, and we'll get to these answers. So Matthias, just kind of hold your thought. If I didn't answer it clearly, then I'll keep trying to do it, because we're going to learn more of this as we go. Does that make sense, bud?
Yeah, okay, thanks.
I love your guys' curiosity, so please don't lose it. Like, keep throwing them at me. This makes this fun for me, because we get to start doing more theoretical stuff instead of just reading the notes. So if I don't explain it yet, I promise I will. Emily asked a question, can you explain one more time where the 0.5 came from? Yeah. So 0.5, I wrote this up here as 0.42. I screwed up. It should be 0.5 because when you flip a coin, you have a 50-50 chance of either one. So 50% should be heads, 50% should be tails. So that was the original, like a population, just grabbing a coin. What's my odds? 50-50. The 42 was what Kate got, and I'm using her name just for fun, was from her sample. So I did a little test. That's the likelihood she would have gotten that kind of size from this average. Something's up. What did Kate do? Or is my sample weird or whatever? So we're kind of starting. You guys are asking great questions. We're kind of starting in there. Emily, does that help with the 0.5? Yeah, no problem. Okay, so without me confusing the ever-loving whatever out of you, try number 3 and 4 with what's there, or just number 3. I'm sorry, I'm looking ahead. So just do number 3. Assume that 30% of students at the high school wear contacts. In a sample of 100, what is the probability that more than 35% of them wear contacts? So check your assumptions, see if you know how to do that. Let's just worry about that first. Can you find the new normal distribution of the sample, or the sampling distribution as they call it, and then do your probability statement. And then hopefully, as you guys have done these a couple times, you kind of understand how the proportions work. Then we'll switch gears and we'll go into the averages, which will make it no more sense for Matthew, because he was asking about the percentages. So I'll give you guys 2 minutes. Just play with it, see what you get. Nobody's going to know you make mistakes but you, unless you share it. Good questions, though, by the way. I do like that you guys ask that stuff. And if I don't know the answer, I will legitimately tell you, I don't know. Let me go find out. Because you might ask a good question, Matthias. I feel like you're the kind of guy that's going to ask a great question one day that I don't have the answer to. That or you or Martin. Martin's one of those guys. Good. And I apologize also if I'm going a little fast, just because I want to make sure we get time to get everything in. All right, so if you're still working on this, keep going. So for that question, Emily, so the 0.07 was on the first question from the population. So it said 7% of people receive loans. So that was my average for both the population and the sample for that one. The 0.42 on the second question is what we were testing. So it's not necessarily the same. So your actual probability statement is usually different than the percentage they give you in the problem. So like here in just a second, we'll see that you have 0.3 for the population's percentage, but 0.35 is what we're testing. So let me read the rest of your question. Make sure I got it. So isn't the same, or are they like we use the same thing? So how can we tell when to use or not? I hope this. Yeah, it kind of makes sense. So let me go through this example, Emily. If you're still confused, then ask, like, rephrase the question. Maybe I'm missing it, and then we'll look at it, because I think this one will help out with it. Because I'm writing down kind of the stuff as we go. All right, so I've got this population of high school students that tells me 30% of them wear contacts. So that's my population percentage. We take a sample size of 100. We want to find out the chance that we're going to grab a sample with more than 35% of them wearing contacts. That's kind of what the whole plan of this is. What's the likelihood that one of my samples of 100 out of the entire population of the high school has in their little group a percentage greater than or equal to 0.35? All right. So we got to check our assumptions first. This part is like muy importante. Number one. Okay. So number one, is my population greater than 10 times the sample size? So is the population of the high school greater than 10 times 100, which is equal to 1,000? So are there more than 1,000 kids at the high school? Again, think big. We're good there. I think there's like 5,000 of you people running around. They're probably not all in the building right now, but just walk down G Hall. It feels like there's just 1,000 right there. All right, so that's assumption number one. Number two, is our n times p greater than or equal to 10? So is our sample size of 100 times 0.3, okay, which in this case is 30, is that greater than or equal to 10? And the answer is yes. So we're good there. All right, number three, is our n times 1 minus p greater than or equal to 10, which in this case 100 minus 0.7, or 100 times 0.7, sorry, which is 70, greater than or equal to. You guys notice something about these numbers yet? Hopefully you're seeing patterns here. They equal up to the sample size, right? So 30% have contacts, then the other 70% or the 70 people don't. So that should be true when you're doing all these. I think that was the case with the other ones too. I didn't point it out, but right, in this case, they're both 100 because the sample size was. Okay, so you're either one or the other. So you got to kind of think of it as like a binomial inside of a normal, inside of a what the heck are you teaching me? It should be all at the same time. All right, so all of these are true. So we can go ahead and continue with the problem now. You need to verify these on paper. This is not just an optional step. All right, so we wanted to figure out now what the distribution is. We know it's normal because we just proved it. We know that the average of the sample is going to match the population to start with. That's all we got to run on. We don't have anything else. So we know that we should get 30% from our samples because we're pulling from a population with 30%. Does that make sense? So I'm grabbing a lot of different groups of 100. If I add up all of their averages, each single group of one unique group of 100's averages, they should come back to the population there. So that's what's happening here. So I don't know if, Emily, that helps with your question or not. These should be the same. What we're trying to find out is this. So that's why those are different. Now, you do have to figure out your new standard deviation, though, because you're dealing with a sample size that's smaller than your population. So you can't use the population standard deviation. We don't really have it anyways, so we have to make adjustments. So this is the square root of p times 1 minus p. So in this case, 0.3 times 0.7 over our sample size, which is 100. All right, when I did this in the calculator earlier, I got 0.0458. That's what I got. If I avoid messing things up on the calculator at the moment, I think I can do this less confusion. All right, so that comes from this. All right, so now that we're good to go, we can actually answer the question, what are the chances that as Mr. Jenikin, I go through the hallway, pick randomly, following my sampling designs from unit 3, what's the chance I go through there, find a sample that's greater than 35%? So I'm just randomly grabbing kids. I don't know if they wear contacts or not. I'm just going to grab 100 of them, following one of my methods, systematic, clustering, whatever. So what's the chance that my group that I grab of 100 has a percentage of more than 35? So that's what we cared to find out. Because maybe that's what I got as one of my results. So I go into second vars, option 2. Okay, we're going to use our lower limit is 0.35 because we want that number or bigger. So upper limit is the infinity. All right, what's my average? 0.3. What's my standard deviation? 0.458. Oops. Don't do what I just did. 0.3, 0.0458. There we go. All right, I press enter and I get 1375. All right, or 76 if you're looking at the note slides because Ms. Nichols didn't round it like I did. So what this is telling me is the chances of me getting a group of 100 out of the population of the high school who 30% wear contacts, the chance of my group of 100 having 35% or more wearing contacts is 13.75%. So if I got that, I don't need to panic. That's a fairly possible outcome based on random chance. I may have accidentally walked into the room of the kids that need glasses. It happens. So no need to panic here. This is within our realm of possibility. We'll learn later that anything less than 5% chance, that's when we start to get concerned. Anything else? Yeah, it happens. You walk into the room and you got what happened. All right, so questions so far. I know this is a lot, but we feel a little bit better about these now that we've seen a couple examples on how to set these up. All right, the means will go a little bit faster because with the means, there's no real assumptions to be made because you already know that it's normal and independent before you get started. So these assumptions for now are only on these proportions things. For right now, we're going to use them again later, but for right now, we're just going to stick with these being here. So keep the examples of that handy. We'll revisit those later on throughout the week. So basically 0.7 was a population sample while 4.2 was what was tested, and that's how they can be told apart when they should be used. Yes, exactly right. Does that make sense, Emily? The way you worded it there makes sense to me. So if not, we'll keep playing with it. All right, so anyways, there's all your answers. She got 1376. That's fine. She didn't round. She went to 0.045826. That's Miss Nichols. She's very precise. You never met her before. So I rounded it and I got 0.1375. Big whoop. All right. At that percentage, who cares? So don't stress it so much. All right, so we're switching gears into the means. We've been talking about percentages. What about averages? All right. Just as a quick reminder, you have different symbols depending on if you're talking about a population, aka a parameter, versus a statistic, aka from a sample. So if we're talking about a parameter, this is the symbol for average, standard deviation, proportion, right? Without the hat, don't worry about the pi symbol. And then we never used this before with our LSLR equations in unit 2, but it is alpha and beta for those symbols. Okay, these are all on your notes, so you don't have to write these down. But I just want to remind you, if you see these weird in your word problems, that's what it's referring to. For the statistics coming from samples, same information, just different letters, because why not? Let's make things confusing. So it's X bar instead of the little U. It's little s instead of that circle with the line on it. It's P hat. And we've used these before, A plus BX in our equation. Okay? So this should be familiar from unit 2. I told you guys, we're putting all the pieces together and we're starting to see the puzzle take shape. So the sampling distribution of a statistic is the distribution of all of the possible combinations. So I'm just reminding you of this, that we've already talked about this. So my normal curve that I'm using for my calculations is all possible combinations. That's why we readjust the standard deviation to fit our new normal curve, because it's coming from every possible combination. Notice, never once did I have to go into the calculator and do 5C2 or anything like that. You don't have to, because you're going to know you're going to do them all anyway. So there's no need to sit there and stress it. I was just showing you guys how that works. Okay, so you'll see that again here in just a second. Don't panic. So now we're going to look at averages, not percentages, but everything's going to be pretty much the same. So we've got these 5 fishies. Everybody's been bringing fish into their ponds here at the steam center lately. And you've measured them, and they're 2, 7, 10, 11, and 14 inches in length. All right, so what is the mean and standard deviation of this population? If you're really nosy on how you want to do it, type it into your list. Do stat calc, 1var stats, boop, you'll get your 2 results. Okay, you don't have to do it right now if you don't want to. Just trust me. It's 8.8 is our average. And our standard deviation here is 4.0694. Again, I just got that by typing it into the list. 2, 7, 10, 11, 14, stat calc, 1var stats. We're good to go. Okay, so if you want to do that later, you can test it, see if I did it right. So Mr. G doesn't want to always measure his whole entire population. All right, we don't always have just 5 like this. So I'm going to take a sample of 2 because I don't know all the stuff about my population in theory. So how many different ways can I take groups of 2 from these fish where order doesn't matter? Okay, so there's 10 different ways to do it. Again, notice we didn't have to do that with the problems. I'm just showing you guys as a way to learn. So we could find all of each samples, all 10 of them, average to calculate it back. And what we're going to notice, just like with our proportions, magic, it's going to be the same. Right? So if you have a percentage from a population, all of the little samples you can take from it that are the same size, same percentage. If you have an average on a population, all the little samples you can take, put them together, add them up, same average. Okay, the averages are nice. They don't change, they match. All right, the standard deviation, though, will. Because again, your standard deviation is based on how big your population or sample size is. So you have formulas again on your notes to help you adjust from one to the other, just like we did with the percentages. All right, if I go bigger and I take samples of 3, again, you will see the average is going to remain the same. It doesn't matter because they're all coming from the same population. They're all the same size. But what happens to my standard deviation? It starts to get smaller. So what happens anytime that the number at the bottom of my fraction gets bigger? What happens to the total answer? It gets smaller. That's what's happening here. So the bigger my sample size, the less standard deviation I'm going to have in my sample. Which, is that a good thing or a bad thing? Typically, it's a good thing. I want smaller standard deviations because what does that help me with my data? More accurate. That's exactly right. I don't have data all over the place. Who knows what? It starts to go like this, and I'm like, ah, there's my center. So typically, a bigger sample size is important. Now, we've learned before we can't be too big because then we're doing the population and we're skewing things and it's not independent. So there's that balance again. How big can I get it, but not too big? All right, so as the standard deviation, as the sample size increases, the standard deviation decreases. So that's something to keep in mind for later if we need that to come into play. But the averages will always remain the same. Doesn't matter if I take a sample of 3, 4, 5, they're all gonna be the same average. All right, so there's your clues there. Now, let's play with these rules here a little bit, do our last examples, and I'll give you guys a chance to have a mental break because I know it's a lot. So rules to remember on our averages. We just talked about these 2. Your averages stay consistent, and your formula for number 2 says your old standard deviation divided by the square root of your sample size is your new standard deviation. So again, as this number gets bigger, I start increasing my sample size. What's going to happen to this? It's going to get smaller, which again, usually is a good thing, usually. All right, we want to, again, keep it close to 10% or less. Okay, so Matthew doesn't want to get crazy and start taking 90% of the population because then he's got no independence. Everything starts to become very, very dependent on what he's doing. Skews his results. Don't do that. When the population is normal, the sampling distribution is also normal. This is the nice thing about averages. It's going to tell you in the word problem, like number 1 here in a second, that the circumference among soldiers is approximately normal. When I see that, no need to do assumptions. If the population itself is already normal, we're good. Yay, no work necessary. All right, that's rule number 3. Rule number 4 says, well, what if it doesn't say? Well, as long as our sample size is sufficiently large, then the sampling distribution will then be considered approximately normal, even when the population itself may not be. What is sufficiently large, you might ask? Well, that is the rule number 4 you're going to fill in here in just a second. That's called the central limit theorem. We say as long as your sample size is greater than 30, you're good. So write that in that little blank there. Anybody who's really interested in where this theory comes from, if you want to do some history because you're bored and got nothing else to do, it comes from a dude, I don't remember his name, that worked in England in the late 1800s and was making beer, basically. And he wanted to provide samples to people to determine which of his new brews were the most popular. So he said, well, how big should my sample size be before I'm confident that what I have is a normal distribution and I can do my percentages. So he just picked a round number at 30, found that it worked, and everybody since then has been like, okay. So does that mean it has to be exactly 31 in order for you to have the CLT? No, it's kind of like just one of those general guidelines. So if Matthew gets a sample size of 29, he's probably still okay. Okay, but if he gets a sample size of 20, we're stretching it a bit. All right, so exceeds 30 is the general rule, and most of the problems will be well past 30. You won't have to worry about it. But just understand that it's just some dude that was brewing, beer in his pub, and he just came up with it, and everybody else afterwards said, oh, that's cool, that worked. And nobody's really challenged it since then. So don't get too caught up on, again, specifics all the time. Rule number 3 was if the population is already normal, then the distribution of X is also normal. So both blanks should be normal with the X bar in the middle. So again, basically what that means, Matthew, is if the word prompt tells me that I'm dealing with a normal distribution already, my samples are automatically going to be that way. There's no need to stress it. We can take any sample size we want, less than 10%, we're good now. But sometimes we don't know what the population is, and so we have to sit there and make assumptions. All right, so let's do some examples in this. I will do numbers 1 and 2 with you. You guys will do 3 and 4, and that'll be it for today. All right, so we got an army reports that the distribution of head circumference among soldiers is, there's our phrase right there, guys, approximately normal. So before I go any further, I already know that whatever my sample is going to be, I've already met that assumption. All right, the population's average is 22.8, and the population's standard deviation is 1.1. So part A is just a good old-fashioned normal distribution probability statement. Nothing fancy on letter A. We just want to know what's the chance that a single randomly selected soldier will have a big old head with a circumference greater than 23.5 inches. So basically, without doing anything fancy, I have my normal distribution already. I have 22.8, comma, and 1.1. And I just want to know the probability that a randomly selected soldier, good old X, like we did in Unit 5, is equal to 23 or more and a half more inches. That's it. So you don't have to do anything fancy. This is from Unit 5 stuff right here. All right, so you go to your calculator. Second var is number 2. This is your lower limit, 23.5. Upper limit is infinity. And then you've got your average and your standard deviation. Done and done. No need to adjust the standard deviation here. We don't have a sample yet. We're just taking a dude. All right. Besides, what's the square root of 1 anyways? For those of you guys who want to use the formula. Just 1. So what is the old standard deviation divided by 1? The old standard deviation. So a sample of 1 is not going to change your stuff. Does that make sense? For those of you guys like, well, how do you know mathematically? That's it. All right. So what it looks like is this. Boom. There's my deal. There's my probability statement. There's my answer. So just general population of soldiers in the army. I go up to a random guy. I pick him, measure his head. I got a 26%-ish shot of finding one with a head circumference of 23.5 inches or bigger. Okay, doesn't seem too crazy. Now I'm going to go and I'm going to grab 5 soldiers. So part B says I'm going to do a sample of 5 now. Not just one guy. I want to do a sample. Because what if I picked a weird guy? So a sample is going to give me a better cross representation of the whole group. So I'm going to pick 5 soldiers. What is the chance they will have as an average a head circumference that is greater than 23.5? So this changes a bit because now I no longer am dealing with the population standard deviation. I have to convert it over to the sample standard deviation. So I'm going to have 22.8 still for my average because that was the original one from the population. But instead of 1.1 here, it's now 0.49193. So that's the little formula from your guys' notes. No, 4 is fine. It's just going to cause the rounding to be off a little bit, but I'm not going to sweat it. So you'll be fine, everyone. So you're going to say, what is the average of my sample of X? Okay, so X bar, or my standard deviation, I'm sorry. So what was the old one? 1.1 divided by, what is my sample size this time? Square root of 5. That's where that number comes from. So you have to adjust this because you're no longer using the population. You have yourself a little sample. Once you get this figured out, everything else is gravy. It's the same steps in the calculator. This is my lower limit. Infinity is my upper limit. This is my average. This is my standard deviation. Lauren said, can I just stop at 3? Yeah. Or 4 decimals? That's fine. It won't make a difference. Now, before we get the answer, would we expect the chances of getting a group's average of this big to be more or less than the individual? Just out of curiosity. Do what? Yeah, so you got a smaller number though, right? Does it make sense why? No? So the chance of me finding one person with a big old head, 26%. The chance of randomly selecting 5 people who average a big old head, much more rare. Because in that sample of 5 randomly, I'm probably going to grab some normal and smaller heads. Sounds weird, I'm saying like big head, small head, but that's kind of what we're looking at. Because in this case, the populations was just a general independent one. This one's based on that sample size. So if we increased the sample size and take like 100 soldiers, then that would become smaller, that number. So we're just comparing it from sample to sample, not from population to sample. Does that make sense? Because the population just has a general overall, like, this is what we found for everybody. But as you start doing samples, if your standard deviation is too big or you're not comfortable with it, then make a bigger sample size. So then a sample of 100 soldiers is going to be much more accurate than a sample of 5. Does that make sense? Kind of, sort of. If you just compare them between samples, that's all you're looking at. Don't worry about, you're not trying to compare the difference between population and sample, because if you think about it, your population is always your most accurate measurement. But then that means you got to count every single stinking soldier and measure their head. But if you're just looking at 2 samples and you're like, okay, which of these 2 samples is most likely to be the same as the population? The larger the sample size, the better. As long as you're, again, 10% or less. Good question. You guys, 5th period wasn't asking nothing. Sleeping. All right, number 2. And like I said, I'm gonna let you guys do number 3 and 4 on your own and see how you guys do. So we got this team of biologists. They've been studying the Pinedale Children's Fishing Pond. X represents the length of a single trout. This group of biologists has determined that the length has a normal distribution. So ta-da, there's our, we don't have to do any assumptions here, we're good. With a mean of 10.2 and a standard deviation of 1.4. So they know that the population already has this. How they know, I don't know. Not my business. They're just telling me, hey, this is what we do. So we're asking, what is the chance that a single trout taken at random from the pond is between 8 and 12 inches long? So do I need to convert or do anything on this one? No, it's just a single, like, there's my population, grab my fish. So that means here we have a normal distribution, because it told me, with an average of 10.2 and a standard deviation of 1.4. That's all already provided to me, given to me in the problem. I didn't have to create that or nothing. My statement is between 8 and 12. That's what I care about. So when I go to my calculator, I should put 8 as my lower limit and 12 as my upper limit, with these as my average and standard deviation. So it's telling me that just grabbing a single fish out of the pond, I have an 84% chance, basically, of grabbing one between 8 and 12 inches, if my average is 10.2. Makes sense, right? 8 and 12 includes the average. That's where most of the fishies should be in size, if my average is 10.2. All right, this is from Unit 5, so are we okay with this? Before we move into the next stage. Okay, so once you got this figured out, then it says, well, what if I take a sample of 5 fishies? I'm not going to catch one. I want to be a little bit more accurate. I'm going to go grab, because I could just grab the really big fish and be completely off. So I want to grab 5 this time. So now, what is the probability that the average length of those 5 fish is going to be between 8 and 12? So you have to convert here. We know that it's a normal distribution because the original population was. So we're good with this being in. We know the original average was 10.2, so we can leave it at that. Question is, what's my new standard deviation? All right, well, what is the new standard deviation of my sample if the old standard deviation is 1.4 divided by how many are in my sample? 5. There you go. So you figure out this number, which is, what did I get? 0.6261. All right, so again, that number comes from here. So now I have this. So I'm trying to solve this question, the probability that X bar, because that's my sample this time, is between 8 and 12. So it's not just X. I'm not just taking one sample. I'm taking an average of the sample. So that's X bar. All right. As you're doing this, Do you expect this average to be more or less than the original single sample? More likely, I should say. What do you think, Daniel? More likely, right? Why is this one more likely and the last one was less likely? What did we do differently? This one includes the average. That's what we did differently, whereas the previous one did not. So the chance of me finding 5 fish with an average between 8 and 12, very, very likely, because what is the average of this population? It's 10.2. So I should be able to go and randomly pick 5 fish that are pretty close to that. So the basic lesson of this was the further away from the average I'm looking for, the less likely a sample of 5, 10, or 15 are going to be versus an individual. Whereas the closer I'm looking for an average, like 8 to 12, the more likely a sample is going to be than an individual. Because again, if I'm just randomly selecting 5 fishies from the pond, most of them are around 10.2. So a sample of 5 should be closer to the average than just the one random. I could get a really big or a small fish. What would be the 95th percentile of a sample of 5? So this is where you use which one? 2 or 3? Number 3, this is your area at 0.95, and you should get your average for your sample would be at 11.23. You'd be at the 95th. Whew. G's tired of talking. I'm sure you guys are tired of listening.
Wait, what was that? What was that last one? How did you work that one?
This one here. So what I'm looking for is the probability that my X bar is basically less than or equal to some number, gives me 95% of the data. Like that's my statement. So what I'm doing on this one, Matthias, is the second bar is number 3.
Oh, inverse number. Okay, yeah.
Yeah, 0.95 here. What is our average for this? 10.2. What is our standard deviation? 0.6261. I'm using the sample one because I'm looking at X bar, not X. And then all percentile questions I told you guys from last year to the left. So what this is telling me at this average, at this sample average, that's why it's X bar, not X, 11.23 inches. If I get a sample of 5 that has this or this number, then it's at the 95 percentile. Does that make sense, Matthias?
Yeah, yeah. Okay, thanks.
All right, very good. So I can reverse engineer it basically. All right, so you guys try number 3 and number 4. I'm going to shut up for a minute or 2, let you practice it. We'll put the answers up on the board, and that is it for them. Number 4 kind of leads us into what we're going to talk about on Thursday, so I'll sum it up for us. All right, it's getting close to the time, so I'm going to go ahead and start talking about number 3. If you're finishing, go for it. And then we're going to talk about number 4 right after that. So you can keep working if you're still working. I just want to make sure I don't hold you guys too much later. So for number 3, we are looking for the soft drink bottler claims that on average cans contain 12 ounces of soda. So that's their population average. X donates the actual volume of soda in a randomly selected can. Suppose that X is normally distributed with a standard deviation of 0.16 ounces. 16 cans are randomly selected with an average of 12.1 ounces. What is the probability that the mean of 16 cans will exceed 12.1? So a couple things to keep in mind as you're going through this so that you're not getting confused. First off, is my population normal? The answer is yes, because it tells me. So everything else is good now. We have to look for that verification. So it has, this is the population's distribution, 12 and 0.16. However, I don't care about the population one because I'm in sample land down here. All right, Mr. G doesn't work for Coca-Cola or whatever. I don't know if that's true. I just went to Kroger and I picked up 16 of these cans. That's my sample size. So I have to readjust my distribution to match my sample. So 0.16 divided by 16, square root of 16. So that's where my 0.04 comes from. You okay with that? Because you have to convert. You can't use this one because you don't work at Coca-Cola. You can only go to Kroger and buy on the other end of it. And I didn't want to go buy billions of them to prove it. I just went and got a 12-pack and then like a few others from friends. So there's my 16. So I want to know what's the likelihood that my sample, which I averaged, is greater than or equal to 12.1. Very small. So it's unlikely that you should get a 12.1 average in your can. So what this probably means is Coca-Cola is off on their average and they're actually giving us more than we paid for. Shh, don't tell them. Because the likelihood of me getting this big of an average from my whole sample, unlikely. But that's okay. I'm happy about that. That makes me happy. That's more soda in my can. It's a small amount, but whatever. I'll take what I can get. Number 4. It says blah, 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 fat and hot dogs, 18 grams, kind of gross. 1 standard deviation gram. Customers, again, aren't going to be concerned with, and I did this the wrong symbol, I'm sorry. No, I did it right. I'm good. Customers aren't going to be concerned with less than, but they would be unhappy if there was more than 18 grams of fat in a hot dog. Yeah, that's kind of weird. So an independent testing organization was asked to analyze a random sample of 36. So that 36 invokes the central limit theorem because nowhere in the problem did it say the hot dogs were normally distributed. So I couldn't do anything until I saw the sample size. So since the sample size is 36, that's greater than 30. Check central limit theorem. These are normal now. Does that make sense? So watch for that. So this is the population's distribution, 18 and 1. I don't work for the hot dog company. I don't work up in Sherman at the Oscar Mayer plant. I only bought 36 of these. So my sample normal distribution is 18 and 0.1667 because I had to adjust for my sample size. So I want to know what's the likelihood of the 36 hot dogs I got being at 18.4 grams or greater. Ooh, gross. 0.0082. So again, this is equivalent to 0.82% chance of that happening. So letter B, does this result indicate that the manufacturer's claim is incorrect? The answer is yes. The chance of me randomly by happenstance, coincidence, whatever, getting a sample with 18.4 or more grams is less than 0.05. We're going to learn about this symbol alpha later. This is our test p-value that we're going to be holding things up as we measure them. So anything less than 5% is a red flag. Sorry, Oscar Mayer, you're lying to me. There's more than 18 grams of fat in them hot dogs. Because I should have not randomly picked 36 and gotten a sample with that big of an average. If your claim is true. So this is what we're going to start talking about in the next couple of weeks. So I hope you guys get into the idea of, oh, we're actually asking questions now and testing stuff and not so much like what's the formula so I can get the right answer and move on. That's your other math classes. We're getting to the fun stuff now. So I really enjoyed this unit. If I get too excited and go too fast, you have to slow me down. You guys asked great questions today. Please continue to do so. As far as the homework is concerned, you should be able to play with that very first page front and back. Let me know next class if we got questions. At home, people, you need your Hershey Kisses next class. Otherwise, you guys have a good rest of your day. Bye, guys. Sorry I talked so much. Can I go back to the work for example 4? Yes, you bet. There it is. Can you send me an email to remind me? Please. And I will gladly do it for you. No problem, Rachel. Let me know if you got questions. Whenever you want. Right now, I'm so behind on grades, I'm not like really upset that people haven't. I was hoping to have everything graded by today. Clearly, I failed on that because it's been chaos around here with teachers being gone. So just whenever you feel like you're ready to go, send me a message and I'll open it up for you. You can take it. Like, I don't really care if you sit at home. If you want to sit at home at 10 o'clock at night and take a test, then you can.
In trouble our first day. We were sitting at 13.
You guys come back though?
Yeah, and then the second day, Saturday, conditions were way worse, but somehow our team just did better in those conditions.
Yeah, because what was the weather like? You guys play locally, right?
Yeah, we were.
So I guess it was a lot more windy on Saturday because they had the wind
Yeah.
advisories going through.
Uh-huh. We were around like Fort Worth area, Byron,
Yeah.
and I did so much better out of nowhere.
Now, were you guys like hitting, so it was going with the wind? or-
It depended.
Yeah.
So we went from 13th to 5th.
Nice.
We were even sitting in 3rd, but then two of our girls
Didn't show up and do the thing.
But like, we managed to come back.
Sorry, just whenever it feels like you're not gonna make it, just tell Anthony I blame him and he'll